À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top. Allumage Vulcain. Allumage EAP. Décollage.
Humans may be the most intelligent life form on Earth, but our bodies can get in the way of our missions. Hey! Oh! And we can't run particularly fast.
And we can't stay underwater very long.
And as for flying, forget about it. But one thing we're good at is dreaming. And the greatest dream in human history is the dream of flying. From the ancient Greek mythology to the Renaissance visions of Da Vinci, we wanted nothing more than to get airborne. People of all eras have gazed up to the starlit skies and dreamed about flying to the moon one day. One of the most vivid dreamers of all was French author Jules Verne. And right now I'm sitting in his former house in Amiens, France. Verne was the founder of modern science fiction. He wrote the first bestsellers to combine scientific fact and adventure fiction. Verne's characters traveled to the center of the Earth, sped around the planet in 80 days, and explored the depths of the sea. One of his masterpieces from 1865 described the dream of space travel to readers across the globe. From the Earth to the Moon, direct in 97 hours, 20 minutes. Listen, 37, 38, 39, fire. An appalling, unearthly report followed instantly, such as can be compared to nothing whatsoever known, not even to the roar of thunder and a blast of volcanic explosions. The Earth heaved up, and with great difficulty, some few spectators obtained a momentary glimpse of the projectile victoriously cleaving the air in the midst of the fiery vapors. Dreamers are able to change the world. Living in the same time as Verne, but miles apart, in a remote village 900 kilometers from Moscow, was a 16-year-old boy. He was very poor, but he had this fascinating dream of using centripetal force to launch a spacecraft from the Earth. Konstantin Tsiolkovsky is now known as the father of rocket technology. But of course, he never saw his dream come true. It took mankind almost a century before fiction became fact. In 1961, Russian cosmonaut Yuri Gagarin ventured into space, becoming the first human being to orbit the Earth. "50-odd years later, I'm 500 kilometers north of the equator in Kourou, French Guyana. This is Europe's gateway to space. Since 1979, Kourou is the spaceport for Ariane rockets. They're launched in an easterly direction. Taking advantage of the Earth's rotation, the rockets get a speed bonus of 1,600 kilometers per hour. This is called the slingshot effect. It is the velocity created by the Earth's rotation around its axis. But that's not the only advantage of the Kourou's launch site's proximity to the equator. Telecom satellites, like the ones that let you watch TV, need a geostationary orbit. They're locked on the same position on Earth all the time, and they move on an equatorial plane. Now, launching from Kourou in an easterly direction means that your satellite is already on the right path. This, together with the slingshot effect, means that you save a lot of fuel. And this is it, the Ariane rocket. It's 53 meters high and it weighs 760 tons. A specially modified Ariane was used to shoot the first ever automated transfer vehicle into space.
With state-of-the-art navigation on board, it finds its destination in space all by itself. But at heart, the ATV is a bit like a delivery truck. The spacecraft, with its heavy payload, docks onto the space station and delivers life's essentials, like food, water and oxygen. And a lot of equipment for the astronauts aboard the space station ISS, which has been orbiting the Earth since 1998.
All these millions of words, written across the centuries and the continents, are all on one topic: transportation. It's a combination of the words trans and portare, which basically means to carry across. Whether it's by horse and cart, bicycle or motor car, it's all the same principle. Humans have always been mad about traveling, and it always makes you wonder why it took us so long to come up with a rocket. People were starting to find ingenious ways to travel across land and water, but no one had made any progress in rising above the surface. But already in the 17th century, Isaac Newton knew what was holding us back. Newton was a very clever man who once wrote that he stood on the shoulders of giants when defining his concept of the universe.
He was acknowledging a debt to his predecessors, people like Kepler, Galileo and Copernicus before them. They stood at the cradle of science. These men flew in the face of common sense with their idea that the Earth might, after all, not be the center of the universe. That was unheard of in their day. Newton tweaked their model of the universe and added some ingenious ideas himself.
The story goes that when Newton saw an apple falling from a tree, he started thinking about why all things fall down on Earth. All objects are drawn towards the Earth by a force we call gravity. Kepler before him had labeled it vigor, and Newton called his law the universal law of gravitation because he believed that his law applied to the entire universe. Ouch! He was right. How much am I attracted to the Earth? Well, let's weigh and see. The force of attraction is measured in newtons. Now, the weight changes with changing altitudes, but by how much? Wow! Here on the ground I weigh 770 newtons. Now, let's move a little further away from the Earth. I might be lighter up there. Here on top of the tower at 146 meters above the ground. Let's see how much I weigh now. It's still the same. I think I must take a more radical step. Here I am, 400 kilometers above the ground, as high as the International Space Station. Oh, hi there! I don't seem to be weightless. In fact, I still weigh 682 newtons, which is about 90% of what I weigh at ground level. The reason is Newton's universal law of gravitation. It tells me the force acting between the Earth and me. In other words, my weight. Little r is the distance between the center of the Earth and me. The reason why my weight has changed so little is because the distance hasn't changed much either. I've climbed only 400 kilometers. It's a bit lonely at the top. I think it's time to go down. Newton's predecessor, Galileo, said that all things, regardless of their weight, should fall at the same speed. Now, that is very hard to believe, don't you think? And sure enough, on Earth, air resistance kind of spoils the theory.
But if you do the experiment in a place where there's no air, like the moon, it should work, as Commander David Scott demonstrated on Apollo 15.
In my right hand, a hammer. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct.
So, what goes up must come down. But that doesn't apply to rockets, surely? Well, not necessarily. This is a sounding rocket. It's launched into space so that scientists can carry out experiments in microgravity, which is another word for freefall.
From here in Kiruna, Sweden, it goes straight up, 700 kilometers into space. That's even higher than the ISS. But whereas the space station stays up there, the sounding rocket just falls straight back down, carrying the data it collected during its flight. But don't worry, it puts out a parachute right at the end so that it doesn't crash onto the ground.
So, staying up isn't just a question of height. It's a combination of velocity and distance from the Earth. Now get that right and you'll have caught the grand prize, a stable orbit. But how fast do we need to travel to stay in orbit? Imagine I'm the Earth. The string is representing the force of gravity and the ball is a satellite. The only thing that is keeping the satellite moving in a circle is the tension in the string. Now take that away and the satellite will carry on moving in a straight line. Now if you change something here, may it be the distance from the satellite to the Earth or the speed of the satellite, then the force you need gets bigger. Whoa! Tired now. So how big is the force we need? Well, Newton already figured out how to keep a satellite moving in a circular orbit. Centripetal force. M stands for mass of the satellite, V for velocity or speed of the satellite, and R is radius, or in our case, distance of the satellite from the center of the Earth. Satellites, like the ISS, are just the same. The only difference is that instead of tension on a string, the force they need is provided by the force of gravity. In other words, the weight of the satellite due to the Earth. But we have a formula for that already. Now, if you put these together, you know exactly how fast you have to travel in order to move in a circular orbit. And it doesn't even have to do with the mass of the satellite, just the mass of the planet and the radius of the orbit.
At an altitude of 400 kilometers, that's a radius of 6,800 kilometers, the ISS needs to move at around 27,600 kilometers an hour. If you could orbit at ground level, you would have to go faster, 28,500 kilometers per hour. Further out, geostationary satellites, you know, the ones that let you watch TV all over the world, they're at an altitude of 36,000 kilometers and they move at a leisurely 11,160 kilometers per hour. Whilst the Moon, 383,000 kilometers from the Earth's center, crawls around at 3,670 kilometers per hour. If we try to go too fast for a particular orbit, the effect is like throwing Newton's apple into the air. It climbs higher and slows down, before falling back again and picking up speed. If you go fast enough, the satellite reaches escape velocity and leaves Earth's orbit altogether. If, on the other hand, we try to go too slow, the satellite loses altitude and begins to speed up before climbing again. If we take that too far, the satellite will enter the Earth's atmosphere, and in a controlled way, this is what ground controllers do when they deorbit satellites and spacecraft. For some satellites, like ATV, the result is that they will burn up in the atmosphere. For others, with a heat shield, it is a hot but safe trip home. Even at an altitude of 400 kilometers, the ISS is not immune to the last wisps of the Earth's atmosphere. It loses about 2.5 kilometers of altitude each month. If nothing were done about this, it would eventually sink deeper into the atmosphere and burn up. So one of the functions of the ATV is to give the space station a small but hugely important push to ease it back to its working altitude. The Ariane 5 is the ATV's carrier. It uses up 238 tons of propellant in each of the 2 solid fuel boosters. It burns it all during the first 132 seconds of its flight. Now, the liquid fuel engine gets through a dazzling 2 tons of propellant every second. This is one hungry and thirsty beast. Cheers. Of course, this hobby rocket is a lot smaller than the Ariane 5, but it works on the same principle. Hot gas is ejected downward at a very high speed, and then the rocket is pushed in the opposite direction. It's Newton's third law of motion. Gas is out, rocket up. All systems go. 3, 2, 1, ignition. Every action, said Newton, has an equal but opposite reaction. Now, if I throw this 25 kilogram weight forward, I will be moved backward. This is not going to give me a whole lot of speed, but it shows you Newton's law in action. I'm throwing this weight, 25 kilograms, forward, and I'll be moved backwards. Look. Now, what if instead of masses, I would throw gas, like a rocket? Whoa! That's only a little gas at quite a low speed. Now, what if I could eject huge amounts of gas at very high speed? Now, that would send me flying. Oh! The best way to show how rocket fuel is ejected is to send this water rocket flying. Now, the water is the gas in this case. Here comes the fun bit. You need a slightly bigger rocket if you want to lift a 20-ton spacecraft like ATV up to ISS. As big as that one, in fact. The 2 solid propellant boosters you see on either side of the rocket deliver 90% of the power for liftoff. Solid fuel isn't the only method of rocket propulsion. There's also liquid. Liquid fuel motors are far more powerful for the given mass of fuel, but they're also much more complex. They need a whole network of valves and pipes and wires and pumps, which is quite a heavy load for a rocket. Like solid engines, liquid rocket motors also burn fuel together with an oxidizer. But here, they're kept in 2 separate tanks. Some fuel oxidizers ignite as soon as they meet each other. Others need a spark to get them reacting. Either way, they're only mixed together when the engine is ignited. Another plus is that liquid fuels burn hotter than solid fuels. This means that the exhaust is ejected at a much higher speed. This gives us a larger specific impulse, effectively the efficiency of the engine. And the great thing about these rockets is
They can be controlled. You can adjust the thrust. Whoa. And stop and start them again. Whoa.
This is absolutely vital for orbit changes and maneuvering after the launch. It's also handy if you're ever planning a return trip to Earth. But how do spacecraft find their way in that vast universe up there? One option makes use of ions, charged atoms. In 2003, ESA's Smart 1 moon probe used ion propulsion. The engines take individual atoms of an inert gas like xenon, knock off some of their electrons and accelerate the resulting ions to very high speeds using an electrical field. Just a little propellant will produce a very big effect. But steady, don't get too excited. Ion propulsion will never be capable of lifting a rocket. That's because the huge exhaust speed gives them great specific impulse, but they still have lousy thrust. It couldn't even lift a piece of paper, let alone the weight of the engine itself. What ion propulsion is good at, though, is moving craft that are already up in space.
There used to be a time when sailors barely had a clue where they were going. They could sail north or south all right, but to find their way east or west, they had to know exactly what time of day it was. For every 15 degrees east or west, time moves forward or backwards 1 hour. So if you knew the difference in time between where you'd come from and where you were now, you knew exactly how far east or west you had traveled. You could tell the local time easily enough from the position of the sun. It's the highest in the sky at noon. The problem was, nobody knew what time at home it was, and all the clocks they had were useless aboard a rocking and heaving ship. Am I right?
This all changed thanks to a man named John Harrison. He was the first man in history to invent a clock that could keep accurate time aboard of a rolling ship more than 2.5 centuries ago. And this meant that sailors could measure longitude accurately.
It took all the guesswork out of navigation.
Knowing the correct time of day meant the difference between a ship landing on the rocks or finding a safe haven. Harrison made a series of beautiful but simple-looking timepieces. The final one won him the grand prize. It was so accurate, it lost only 5 seconds over 2 months. This was good enough to ensure you could arrive within 2.3 kilometers of your port of destination. Impressive, but you can't beat the latest in time technology, Galileo, Europe's own global positioning system. The atomic clocks on board Galileo navigation satellites lose only 1 second every 20,000 years. As if that's not precise enough, cesium clocks on the ground continually synchronize them so that they only lose 1 second in 100 million years. Now that's what I call accurate. Galileo tells you exactly where you are going, give or take 10 centimeters.
Where am I? Well, to know exactly where I am, my sat-nav needs to listen to at least 4 satellites of the many that are out there. It then calculates the exact distance from me to each one of them. And with that information, ta-da! I know exactly where my bike and I are on Earth. The basic principle is the same as it used to be for maritime navigation in the past. The precise difference in time between 2 places equals their relative distance. Let me put it this way. Here is my satellite. It sends a radio signal at regular intervals. It's a sort of SMS containing a very precise atomic clock time. Now, my sat-nav here receives the signal and compares it to its own somewhat simpler clock on board. The little computer inside can now calculate its distance from the satellite. But imagine how many places there are on Earth having that same distance. So one satellite is hardly telling me anything. Things get a lot better if you add a second satellite. But calculating two distances is still not enough to tell me where I am. I could be here, or here, or here. Will a third satellite then complete the puzzle? In theory, yes. But I'm afraid in reality things are a bit more complicated. The clock inside my sat-nav is by far not as accurate as the ones up there. And to make things worse, the signals of these satellites travel through different layers of the atmosphere, causing delays. Help! We need a fourth satellite! Or even more!
Luckily, the software inside the sat-nav takes into account all these variables and eventually, within nanoseconds, determines my current position on Earth or in space. It compares the data with the maps it has stored in its memory to provide me with all sorts of useful information, such as how to go to my next destination. ATV also uses a similar system to find its way through space. The unique thing is, an ATV can work out its route to the space station ISS all by itself. It uses an array of navigational techniques depending on how far it's away from its destination, hence the name, Automated Transfer Vehicle.
GPS and an optical device called Star Tracker is used to point the ATV in the right direction. But how? There are billions of stars out there. Well, it uses 57 bright navigational stars and compares them to the maps inside its computer. It works a bit like this.
Will Leo fit? Nope. Taurus, maybe? Wrong.
Could it be Ursa Major? Yes!
Direction and roll angle confirmed. When the ATV is within 250 meters of the ISS, it's time for the ATV to switch on a videometer for high-precision docking.
The videometer uses pulsed laser beams, and these beams are bounced back by mirror cube reflectors on ISS. An ordinary mirror reflects the light at an angle. I'll show you. Now, let's get the laser beam in. And here you go. However, a mirror cube always reflects the light back to where it came from.
This is a retro reflector and it has 5 mirror cubes. They reflect the videometer's laser pulses back to its sensor. All we have to do is look at the size and shape pattern that is reflected back, here shown by red dots. As long as you can see this correct orientation pattern, like the number 5 on dice, you know ATV is on the right track. But if the image tilts, beware, the system is telling you that the ATV itself is rolling, tilting or turning. Not good.
When all goes to plan, ATV and ISS make contact at a relative velocity of a few centimeters per second. A slow and gentle embrace, 400 kilometers above our heads. But if you think about it, this embrace is happening while both vehicles are orbiting the Earth at a dazzling 28,000 kilometers per hour. It's hard enough docking 2 fingers in mid-air while I have my eyes closed. And I'm standing still. The ATV is the latest, but certainly not the last chapter in the history of space exploration. There are 4 more ATVs planned for the future, and they're being built here in Bremen. This is a model of an ATV that may carry humans to the ISS one day. The search is now on for new forms of spacecraft propulsion, especially for missions deep into the solar system. Maybe giant solar sails are a possibility, or nuclear-powered rockets. These ideas are both bold and old. Writers like Jules Verne suggested these options a long time ago for rockets flying to the moon. This was considered a crazy idea then, but today, several future plans are being made for people to live on the moon. The Russian space pioneer Konstantin Tsiolkovsky already hinted at that 100 years ago by saying, "Earth is the cradle of humanity, but you can't live in the cradle forever." There are still plenty of puzzles to keep space scientists occupied. And humanity is still dreaming.